So now let's look at the propagator. Or the time evolution operator. When the Hamiltonian is time independent, okay? So we have written the time evolution operators as t, comma, t0. When the Hamiltonian is time independent, then it becomes a function of t minus t0. That is, it only depends on the difference in time. Okay, so we want to find out the explicit form of this operator when the Hamiltonian is time independent. When the Hamiltonian is time dependent, it's a much harder problem, and it can only be solved perturbatively via what is known as the Dyson series. We won't have time to cover that in this course. So I have done this in some form or another, but I want to do this again. It is so important. So this is Schrodinger equation in its abstract form. IH bar, the derivative, the time derivative of some state is given by the Hamiltonian operator acting on that state, right? So, but the initial condition is that at time t equals to t0, this state starts off at the state alpha t0. This is my initial condition. And so the time evolution operator, what it does is that acting on alpha at t0, it gives me the state alpha at time t, where t is a time later than t naught. So this boundary condition can also be written as u t comma t minus t0 when t becomes equal to t0. This becomes the identity operator. So now what we can do is that we can take this and insert it into this equation. Then what do we get? We get I h bar d by dt u of t minus t0 times alpha t0 is equal to h u t minus t0 alpha t0. So see that here, this derivative acts on this guy only. It does not act on the state. So this equation is true for all alpha, all initial conditions. Therefore, it must be true as an operator equation. Therefore, we derive in such a way an equation for our time evolution operator. Now, U is a unitary operator, and we know that any unitary operator can be written as exponential of I, some parameter. Let's take that parameter to be t minus t0 here. Well, it is that parameter, times some Hermitian operator, which we are going to call x. So x is Hermitian, which means that U is unitary. You know that? So now if I put this ansatz into this equation, what do I get? I get I h bar. The time derivative brings down a factor of I and x. And then U t minus t0 stays because it's an exponential operator. And then this is equal to h u t minus t0. Now we can multiply this equation, multiply this equation with u inverse of t0, which is the same as u dagger of t minus t0. If I do that, then I get minus h bar x is equal to h. And therefore, I see that my time evolution operator u t minus t0, in the case when the Hamiltonian is time independent, is given by e to the power minus I t minus t0 divided by h bar h. Okay? Is this clear? Is there any question about this derivation?
No question, sir.
Okay. And see that the limit in which t is equal to t0, this u becomes the identity operator as required by the boundary condition.